So yeah, this is Ruiqi from Australian National University, and today I will introduce our paper, Unsupervised Novelty Characterization in Physical Environments using Qualitative Spatial Relations. So first, for the background and motivation of our paper, we know novelty is everywhere. So for example, in this Angry Bird game, usually the bird will stay and die after hitting a pig. But if we introduce a novelty by increasing the bird's bounciness, as this video below shows, the bird will be bouncing back after hitting the pig. So detecting and characterizing this kind of novelty is very important for AI agents to operate reliably in open world environments. But our current approaches have not succeeded at handling those novelties. For example, the expert systems are brittle and rely on human efforts a lot, and the deep learning methods are black box and hard to explain. So consider this situation, we aim to propose an approach that can describe the environment and characterize novelties in an automatic and human understandable way. So based on this motivation, we propose our approach is automatic and unsupervised approach consists of two steps. And the first step of our approach is the normal environment description. So as this figure shows here, we observe state transitions from a sequence of frames from the environment without novelty and merge those state transitions into clusters and convert the clusters into actions as a base model. And the second step, the novelty characterization. Since we already have the base model here, when facing the environment with novelty instead, we define the repeated uncovered state transitions, RUS, as the recurring presence of state transitions in this normal environment that's not represented in the base model. So based on this RUS, they can be regarded as the actions of the novelties for characterization. So that's our whole procedure of the approach. And next, I will explain this procedure of the two-step approach accordingly. So for the first step, the normal environment description. First, for converting the frame observations in a symbolic representation which human can understand, we use state transitions for this representing. Here, if we use qualitative relations as this representation of a state of two objects. As shown in this right figure, we use four qualitative spatial relations: the topological relations, movement relations, direction relations, distance relations, plus one object existence property. So based on this five relation state representation, a state transition for an object type pair occurs when at least one of the five relations changes between consecutive states. So next, with these state transitions generated from the last step, we assume similar state transitions are caused by similar actions. So we merge the state transitions to get a set of clusters for further extracting actions from them. So here we create a two-stage clustering method. We call them graph-based hierarchical clustering, GHAC, to cluster those state transitions. In the first stage of the clustering method, based on the conceptual neighborhood diagrams of each QSR, we calculate the conceptual distances for the five relations of the two state transitions as their overall distance. And by linking the nearest neighbor for each state transition, the linked neighborhood graphs are our initial clusters. For example, in this graph with four red dots here, it is one of our initial clusters with four state transitions inside. And then in stage two, we iteratively merge the two most similar clusters from stage one until there's no such two clusters can be merged. Here we define the similarity of delta aspects of state transitions in the two clusters are no less than tau, then they can be merged, where the delta and tau are predefined. Shows here, for example, these two initial clusters, or say graphs with red dots and yellow dots, they can be merged as the clusters with blue dots in the stage two. So the output of our GHAC is a set of clusters, and each cluster is a set of state transitions. And then next, based on the generated clusters from the last step, we format those clusters into a PDL-like action representation. So these actions are the base model we want. As this rectangular example figure shows here, for a generated cluster C, which contains five state transitions inside, we calculate the proportion of the most frequent relation pair of the five aspects as this eta C shows here. And by comparing the proportion with our predefined tau, here we predefined the tau as 0.7, we can see like only for QDC, the proportion is lower than tau, which is 0.6. So we believe there's no representative QDC relation change in the cluster. So it can be regarded as an arbitrary relation change, marked as star in the representative state transitions RCC here. And then by converting the RCC into a PDDL-like format action representation, as shown here, the parameters are the types of the two objects, and the precondition is the before state of RCC, and the effect is the relation changes from the before state to the after state. So by doing this on each of the generated cluster from our GHAC, we receive a set of actions as our base model from the non-normal environment. And this is the procedure of normal environment description as the first step of our approach. And the second step of our approach is the novelty characterization. Now we already have the base model from the non-null environment. So given a new environment with a novelty inset, as this input 2 shows here, we still detect states and state transitions in this new environment in the same way and check if each of the state transitions generated from this new environment is uncovered and appears repeatedly, as the repeated uncovered state transition Rus that we introduced before. So here we define a state transition as covered if and only if there exists an action in the base model that the before state satisfies the action's precondition and the action's effects can be applied to the before state in a way that yields the after state of the state transition. And also the object type pair of the state transition must be the same as the parameters in the action. So now, since we already have a set of Rus here, we can use those Rus for first nullity detection because Rus will be more frequent when the nullity occurs. And also for nullity characterization, because we can create novel actions based on Rus by converting those Rus into a PDDL-like format, just like what we did before. So that's all for our proposed approach. And the next step, we will evaluate the approach by conducting several different experiments. The first one is the base model construction. So for this experiment, we have create a data set based on the Angry Birds game. So the training data is state sequence from 170 standard levels. We play them 10 times using a random agent, which means the agent will shoot randomly. And the test data is another 30 standard levels. We play them 3 times using a naive goal direct agent, which means that the agent will only target to the peaks. And also we propose 2 evaluation metrics. The first one is the action validity, which is the fraction of actions in the base model that can be found in both training and test data. So it indicates whether the action in the base model are valid and can happen for real in the game. And the second one is the coverage, which is the fraction of state transitions in the test data covered by the base model. So the coverage measures the generalization ability of the base model. And we also have 4 different baselines for comparison. The first one is HAC, which is also created by us by removing the neighborhood graph step from our GHAC. And the second one is cube space action autoencoder, which is a deep learning clustering algorithm from Masataro Asai's 2020 paper. And the last 2, K-means and LSA, they are 2 most popular clustering algorithms used by the same paper, Duckworth's 2019 paper. So let's see the result of the first experiment. Our target here is to achieve a high coverage and validity with a relatively small number of actions in the generated base model. So we can see from the table, no method dominates in the 3 criteria. But first, we can see GHAC achieves better coverage and validity trade-off and smaller number of actions than HAC. And GHAC has a higher coverage and validity than both K-means and LSA. And although AAE has the best coverage, which is only 1.1 higher than our GHAC, but its validity is extremely low. So it means it generates model that overgeneralized. So overall, we can see from the table, our GHAC achieves the best performance. And for the second experiment, based on the best performed base model, which is generated from our GHAC, we evaluate its ability of detecting a nullity by comparing the different number of Rus in the environment with and without nullity. Here we introduce 5 novelties. For example, the red bird with increased responsiveness that we introduced before is one of the novelties. And novelty 0 represents the environment without any novelty for comparison. So given the 30 levels in the previous test data, we introduced novelties into those levels and randomly select NL levels from these 30 levels. And by repeating this selection 100 times, we check the cumulative percentage of this 100 selection with respect to the number of rusts. So given different NL as 5, 10, and 20, we can see from this bottom figure, 20 levels are already sufficient. So by only playing 20 levels, the number of rusts of the environment without nullity, which is shown in this red line here, are always less than 10, which is almost always smaller than the number of rusts from the environment with any of the other 5 nullities, as shown as the other colored lines here. So it means we can detect if there is a nullity in the environment by comparing the number of rusts with the non-novel environments, because usually the non-novel environments contain fewer rusts. And the last experiment is the novelty characterization. So by checking the overlap rate of the novel actions from the environment with each novelty, as this table shows here, only the overlap rate between novel actions of novelty 1, which is NA1, and the novel actions of novelty 2, which is NA2, are 0.36 and 0.22. All the others are very small numbers or 0. So it means only NA1 and NA2 have partially overlapping characterizations, because actually visually, some of the actions of novelty 1, which is the red bird with increased responsiveness, and novelty 2, which is the red bird with increased linear drag, some of their actions are similar. So it means our action-based novelty characterization can not only distinguish nullities, but also see similarities between them. So in conclusion, we are the first one that can automatically describe actions in the complex physical environments based on the symbolic representations of observations. And our proposed approach can detect and characterize nullities in this kind of physical environments by extracting their novel actions. And since we already test our proposed approach on non-reverse game and compare with other state-of-the-art methods, we can say our approach achieves the best performance. So that's all for the presentation. Any questions?